Forgot to record, just started it. All right, closing out. So the overwhelming answer is not clear. How many sig figs should we have in this? 4. Why 4? Because the lowest number of sig figs in all of these is 4 sig figs. So if that's the case, I'm going to guess that this is the right answer. 57%. I guess everyone's close. Maybe you guys were running out of time and you clicked in a shorter answer. I'm hoping that's the case and that you do know how to use your sig figs. What would that ratio be? What would Q be at time 0? What is Q at time 0? Concentration of products is 0 divided by something. Which one can you not do? Okay, so 0 divided by something is okay. So this would be 0. So then in order to get to equilibrium, we obviously see which way it goes, but this is a graph that helps us kind of make sure we connect that prediction visually. So that's a really good question. So for this reaction, can we ever get all products? It'd be really hard. How do we get more products?
Different ways.
Different what? A different reaction?
Well, different ways to do it.
Okay, so what are some of the ways that we could push this to all products or close to all products? What do you guys think? So if we added a catalyst, it would lower the activation energy, but would that change the relative position of reactants and products?
Would it be harder for it to go from products back to reactants if the catalyst only works one way?
So it would lower the activation energy, which changes in both directions, and maybe the proportionality of that would be different. So we'd have to measure K forward and K reverse to see how that would change it. What other ideas?
We knew which A or B was limiting, and we could add more concentration of that one.
Okay, so we could add more of one of the reactants. And if we added more of one of the reactants, we would drive the reaction forward. What's another way we could make more products?
Temperature.
Maybe temperature, maybe not. Some reactions get slowed down or go in the opposite direction when we end up heating them up. What are some other ideas? How could we get more products?
Pressure.
Maybe pressure, depends on the compound. It's another guaranteed way we can make more products. Goes along the lines of what Don said. Don said add more reactants. What's another way? If we add more products, is that going to drive the reaction this way? So if we can remove this somehow, maybe it's a solid, and maybe it's a reaction, there's lots of water, right, and everything's reacting, but the product is a solid, or we can make it a solid, and it's no longer in solution, then that means the reaction is, going to keep going towards products. So there's a number of different ways, and the Chatelier's principle helps us describe some of those, and we'll be talking a bit more about that next week. So let's talk about another reaction. This is one of the ones that we've been talking about in combustion engines. So when you have N2O, saying it backwards, NO2, noxious gases formed from our cars. Tatiana, you all right? So when our combustion engines go, we have nitrogen gas, we have oxygen gas, and they produce NO2. But NO2, when those molecules collide with each other, can generate N2O4. And that reaction is reversible. So we will write that out as a balanced equation, and the equilibrium arrow shows the reaction can go in both directions. So what we want to think about then is if we start with all NO2, what ratio are we going to get at equilibrium? And here's our little animation that helps us answer this at this temperature. So we started with all NO2s. What's our equilibrium constant? Click in your answer. What's our equilibrium constant? If this is frozen at equilibrium. So this one we started with all NO2. What do we get? Anyone could click it in? So based on the way that this, based on the way that this reaction's written, what is our K? Alex, what's our K? What's our KEQ expression? What's the KEQ expression always going to be? McKenna? Okay, so that is one of them, but we don't know anything about our equilibrium or our rate constants here. So we're just going to focus on concentration of reactants and products. So what goes on the top? Claudia? 2. So it's concentration of something on top, concentration of something on the bottom. There's stoichiometric coefficients involved. Who wants to help me out? What is that expression? Don?
Concentration of NO2
raised to the second power over
concentration of N2O4.
So in this case, we actually started with all products, right? And the way that the reaction is written, NO2 is what we started with. We ended up with a mixture that was, what is the ratio you found? 2 to 1? Is that what you guys found? And I think...
I did 2 divided by 1.
Yeah, I found 1 to 3.
Yeah, I think the ratio is 1 to 3. So it should be 3...
That's because you wrote. It's going from NO2 to N2O4.
So it's always that ratio. So I'm not saying that... So the ratio would be 3... So we have 1, 2, 3, 4... We have 12 of these. Not true. So it all depends on, so that's a good point. So as I. Bailey pointed out, if we're talking what is a reactant and what is a product, that is all defined by the way that our chemical reaction is written. So in this case, we started with all products. It isn't a reactant because we start with it. It's a reactant defined based on how the chemical reaction is written. So in this case, we would have our KEQ would be 3 squared over 1, which is 9. How is that going to change if we start with all N2O4 instead? What's going on?
I put percentage, like a actual K value.
Oh, so you answered the question that was at the bottom there?
Yeah.
All right. I think that we're probably confusing you guys by doing K and having a different question on there. Is that fair?
Wait, is that question not what we're answering?
No, it wasn't what we're answering. I said something different than what was up there. I asked for K, and you guys typed in the ratio, I think. So I'm not... Okay, you guys know how to find the ratio between products and reactants. Do you know how to use that to determine what K is once the reaction gets to equilibrium? That's what I need you guys to be able to do. And then the point is, well, what if we started with all N2O4 instead of all NO2? Are we going to get a different ratio? What do you notice? So basically we're saying if we start here, we're going to get this ratio. If we start here, we're still going to get that same proportion. So no matter where we start, no matter what Q we have initially, that value of K is always going to be a constant, regardless of what we do to the reaction in the meantime, as long as we don't add a catalyst or change the temperature. So let's take a look at what that ratio is. So this reaction has reactants and products. And so what I've done here is I've said, okay, if we started with all N2O4 on the far left side, and no NO2, we have our initial concentrations. And then as time goes by, we ended up with a certain amount of N2O4 and NO2. So what a lot of people do, the first thing they do is, well, let's just find the ratio of products to reactants. And we find a certain ratio. And then we try the mass action expression, which is K. And we find a different value. Let's look if we start with a mixture of reactants and products. We start with a different mixture. different mixture, and if we start with only NO2. Which one of those ratios holds constant regardless of what we start with? So Alex, which one of these comparisons would you want to make in order to make a prediction about what's going to happen with the reaction? Pauline, you want to help out? So if we're using real experimental data, then we want to look for trends, things that are very similar. They don't have to be exactly the same. So basically we're saying if we have all these different experiments, the way that we figured this out wasn't a whole bunch of brilliant people picturing what happened to molecules. They looked at a whole bunch of experimental data and said, what trends are there? How can we use those trends to make predictions? And what they found was no matter what ratio of these things we start with, we end up with different ratio between these two, but the mass action expression seemed to always stay constant. So it's almost one of these empirical evidence. When you find something that holds true, a trend that holds true, we know that we can use that then looking forward to figure out what the ratio of reactants to products is going to be. And it's not just the ratio of reactants to products. It's the ratio of products raised to the stoichiometric coefficients divided by concentration of reactants raised to stoichiometric coefficients. So we're never going to end up with the exact same concentrations of everything, but that ratio should always be the same. What questions do you guys have? You want to try to use this some instead of just look at numbers? All right, so I want you guys to look at these concentrations, and I want you to tell me whether this reaction is at equilibrium or not. This is the same temperature that we just had for that last set of experiments. Did anyone write down the equilibrium constant that we get? I'm going to go back so you can write it down. All right, so at this temperature, you guys should know what the equilibrium constant is based on all of this data. Does everyone have it? Tatiana, what's the equilibrium constant at this temperature for this reaction? 4.6 times 10 to the negative third. I would say, we could probably say 4.62 or 4.63, but I don't know if we're going to be accurate enough for that, so maybe 4.6. Okay. So, tell me, is this reaction at equilibrium? Ten more seconds. Dana, how do we tell if this reaction is at equilibrium?
Plugging in the concentrations.
Okay, so if we do that, what do you find? Equals 0. So is 0 equilibrium?
No.
Not for this reaction at all. Did anyone do this without crunching any numbers or putting anything in an equation?
I did, but I picked A. I looked at the table and I found those numbers that you gave us and went over, and it was 4.6 something.
So careful, careful. What these numbers were was initial concentrations.
Is that not what
By the time that they got to equilibrium, they were not that anymore. This is the equilibrium concentration.
So the numbers on the other side are those middle boxes?
So if we go to this slide, these numbers are saying, okay, if this is the concentration we have, are we at equilibrium or not?
So those aren't the initials.
These are the initial concentrations. If this is our initial concentration, we know that this does not equal K. Q does not equal K. So we'd have to compare those two. But what I was getting at is there's a way we can just look at this right away and say that we know this is not at equilibrium. Why?
Because the product is 0.
Okay, so if there's no products, then how do we look at K and determine that there should be some? Well, this is actually a really, really important point that you're getting at. So if we know, this table's going to flip on me. If we know what K is, how do we look at this and say immediately, I know that we're not at equilibrium? How does that 0 tell us that? Talk to your group for a second. How does that 0 tell us we're not at equilibrium? Whatever you guys are saying. Yep, so we're starting a reaction. We may be at equilibrium, we may not be. How do we look at that number and tell that we're not at equilibrium? Okay. There's something more fundamental about it that I want to get at. So who has a really good idea how we look at that and our K without doing a calculation and how we say, I know immediately that this reaction is not at equilibrium? Demetrius?
Because isn't there there's no product concentration, so it can't possibly be at equilibrium if there's no concentration product.
Well, maybe the reaction just doesn't work, right? So maybe I take diamond plus water, and I say I'm going to make some random stuff out of that. The reaction doesn't work. So what would K be in the case where the reaction doesn't go at all? It would be 0. Do we have a K of 0? So by looking and seeing that we have a K value that's non-zero, we automatically know that some products have to be formed. You guys follow? This tells us we have a K that's non-zero, so there must be some of both reactants and products. Because there's not, this reaction is not at equilibrium. Does that sit okay with you guys? Taylor doesn't like that? Can you ask a question to help clarify? Can anyone help try to re-explain that? Smells like chicken and sweet potatoes in here. So, Megan, can you try explaining nice and loud for everyone?
So the only way that K can be 0 is if one of them is 0. But we know that K isn't 0, so if they're not, so if they are 0, then it's not equilibrium.
Okay, so just by kind of looking at number comparison, does anyone else want to add to that? For how we know, how we can tell because K is not 0 that the reaction must not be at equilibrium.
Can you think about this type of graph and like when the products are at 0, it's in the kinetic phase, so it's still working its way up to equilibrium. And and at time 0, that's never going to be equilibrium.
Yeah, so by knowing that our K is not 0, that tells us that at equilibrium there is some of both. And so we know that we must in the kinetic phase if we have something that doesn't include any of one of the two. So we can catch up and maybe talk through it after class. Jordan.
One question. So
Sure.
say, and if you did have, you'd still be able to, is this at any time or just at 0?
Let's do another one. So this is at a particular time with a particular concentration. So we could calculate find Q, right? So let's ask one question before we move on to another set of concentrations. With the Q value that we do have, let's answer that second clicker question. Given time, the reaction will generate more of reactants, products, or neither.
At equilibrium or
At these concentrations that are shown at the initial. So with these initial concentrations, this is the Q value that you guys all calculated, 0. This is our equilibrium constant. So the question is, to get from Q to equilibrium, does that mean we're going to generate more products, more reactants, or that we're not going to have a net change? Good question about this, right? Everybody clicked in, what's going to change? Closing out. Thomas, you want to share your thoughts? Why are we going to produce more products? Okay, so we can compare Q to K numerically and say that Q is going to get to K, which means that the numerator has to get bigger. Did anyone do this a different way?
I said that it would generate more products because the products started at zero, and since we already know the reaction is actually happening, we have to have more products.
Great, and that was the point I was trying to get at just a minute ago. That if we see our products are zero, and we know the equilibrium constant doesn't have zero products in it, that the reaction has to generate products in order for that reaction to go forward. And that process, that thought process, is critical when we start talking about acids and equilibrium constant for weak acid. So, because the equilibrium constant is much greater than our Q, that means the reaction is going to go towards products. That means that the numerator is going to have to get bigger in order for that number to get bigger, which means we're generating products. What about these conditions here? So now we have a non-zero number on both the reactants and the product side. You guys need to determine whether, let's answer the first clicker question. Is this reaction at equilibrium, yes or no? And then once you've decided if it's equilibrium or not, then you need to decide what direction it would go. If it's not equilibrium, or if it is, then we'll click in the second question in a second. Should be. Hit the blue button if it doesn't register.
It says close.
You're wrong. Sorry, I'm not too good at technology. Unless it's Harley.
That's not Shane, that's more.
Yeah, that's the Bailey. It smells terrible. How do you guys put up with the smell all the time? All right, everybody clicked in? So Brooke, how'd you answer this question?
We said yes because when you plug these numbers into K, it
Okay, so if we find Q, we find a number that is very close to K. Is that close enough? I'm happy with that. It's within the range of error that we saw with the numbers before that we said were at equilibrium. So I agree. That reaction is at equilibrium.
Just so we have a point of reference, if we saw this on a test, if they're between point, like the 10th decimal, then you're saying that it is the same?
I would not give that level of detail. You guys would have to make an argument based on what you see here and decide whether it's rational to say that that is at equilibrium or not. And you guys have been doing a lot of experiments and talking about error bars and those kinds of things, so you need to figure out, in the orders that we're talking about how big K can be and how small K can be, is this close? That's what you have to decide. So if that's the case, if those two are equal, then answer the second clicker question. What question do you have, Thomas? Say again? Hold on, guys. Can we get everyone back together? Thomas, can you go ahead and answer the question? Did we have 6 different values? What do you mean? What were the values? Yeah. So there was a variety of them, and we said, well, somewhere about the middle, but it really, I think going back to, I can't remember who it was that said, was it Tatiana? Salma, one of you guys? That said 4.6 would really be the equilibrium constant that we could use. And so 4.6 to 4.7, somewhere in that range, would be a reasonable value, times 10 to the negative third. And so if we have these values, then we're not going to create more reactants or more products, but the reaction is going to have an equal rate of reaction forward and back, so the total concentration doesn't change.
Like, if your equilibrium constant was 4.6 times 10 to the negative third, and then you got a Q of 4.67 times 10 to the negative third, like, is that a pretty big difference for really small particles?
So let's write it out. 4.63 times 10 to the negative third is 0.00463, right? Versus 0.00467. How big of a difference is that? Could you calculate the percent difference between those?
You gotta do significant figures. What if you had to do 4.6 then 4.7?
Yeah, so 4.6 versus 4.7. If we're talking about chemical reactions, billions and billions and billions of molecules that are interacting and becoming products and reactants, is that difference significant?
No.
That's what you guys have to be able to determine. I know you don't like that. This is not statistics, but you guys should be able to apply at least some basic values of statistics in order to determine whether differences are reasonable or not. All right, what about this one? 15 seconds, answer. Is this at equilibrium or not? Close now. Valerie, what do you think? Why is it not at equilibrium? Okay, so one, if we find Q, it's undefined. But other than that, McKenna, why do we say that this reaction is not equilibrium?
Because if K value isn't zero, so the reactions are
Okay, so it's not 0 or undefined, which would be the two extremes. So what does that tell us about, what do we have at equilibrium? So who wants to help out? Maybe I'm not asking a very clear question.
From the 0.00 and the 0.2, I would think that equilibrium, well, I would just think nothing, because how can you even form products without reactants?
So in this case, we only have products.
Yeah, so like,
When those come together, they form the reactants. Is that what you're saying?
no, I just thought that if you have products, like say if you're like, okay, these reactions are right here, you have 0 reactants and 0 products.
We don't have 0
I
products.
mean, you have products. I would think that you have to have some type of reactants to get to the products. Like, is it just saying that at this stage it's already at products?
So where are we on this graph here?
Like Q?
We are way over here. Does that mean we can't go backwards? Okay.
Your KQ is real small, so it's all the way to the reactant side, but you have no reactants.
So our KEQ in this case is way over here, even further left. And we're saying in this case we're all products, so that reaction is going to go all the way until it reaches reactants.
I'd like to try and make a reference back to the equilibrium dice that we did what was that, last week, right? Do you guys remember that? You were rolling dice and you had different ratios and different rules to that game you were playing. Do you remember as you were progressing, it kept fluxing, right? Kept fluctuating back and forth until it evened out eventually. Same thing happens in real life in an actual experiment. So it's going to fluctuate until it reaches equilibrium.
So if you're expecting to get a perfect number when you get to equilibrium, you guys saw yourselves, you generated the data that shows that doesn't happen. And that was with a very small number of particles that are all in a very defined set of rules, right? In real life, there's a lot more complicated things that are happening. So thanks. Let's look at one last one. What about this set of initial concentrations? Like black stuff all over me. Miata, I'm going to call on you for Q. Ready? All right, closing out. So Miata, did you find Q?
Yeah,
What did you find for Q?
4.63 times.
So you found 4.63 times 10 to the negative third.
Yeah.
But those are different concentrations that we had up here. How's that possible? How can this be the same K as this?
I mean, it's a constant.
It's a constant. So what does that tell us? What do we know about this mixture of reactants and products?
We have more reactants than products.
Okay, so the way that the reaction's written, we have more reactants than products. And we know that that mixture is a stable mixture at this temperature. So are we going to generate more reactants or products if we let this go over time? We're going to generate more products. Everybody agree? Why? We're at equilibrium. Products are going to generate reactants. Reactants are going to generate products, but we're at equilibrium. And I can't remember if there's one more or not. There is one more. All right. So we're at equilibrium here, right, guys? Why? What's the misconception that I just pointed out, Sarah? Why is that a misconception? Why is it wrong to say we're at equilibrium for this one? Because it's not at equilibrium, okay. So why might some people automatically say that this is at equilibrium, Jose? Me?
Concentrations are the same.
Well, the concentrations are the same. Isn't that equilibrium? Okay, so what did you guys find for Q for this? 0.065 is our Q value. That's not the same as K. So this reaction is not at equilibrium. What direction will this reaction go to reach equilibrium? Go ahead and answer that second question. In order for the last reaction to reach equilibrium, what would change? That's Q. So we've got to be really careful. We're comparing this value to what? To this. So is it bigger or smaller? Mommy, in order to determine if this reaction is going to go towards more products or towards more reactants, what did you compare? How did you decide?
I saw that.
So if Q is greater than K, then it's going to shift to, which did you say? Why? How did you figure that out? Is that like a memorized if Q and compared to K then this? Or can someone try to verbalize how we look at the relationship between Q and K and determine where it's going to go?
Since K is products divided by reactants, since K is smaller than Q, you would need to increase the denominator in the ratio.
Great. So I like that looking at the relative numbers here, and that we know that this number is bigger. So that means that we need to decrease the size of it. So we need to take some products, move it to reactants, make the denominator bigger, the numerator smaller, and that will decrease Q, moving it towards K. The other way to do that would be that if we had our Q value compared to K, if Q is bigger than K, that means we're going to be moving in that direction as well. So a number of different ways you can think about this. All right. Questions? You just say yeah?
Oh, no.
All right. I have some hidden practice problems that you guys can work on to figure out Q versus K. But for the last part of class, we're going to be doing this problem. So I want you guys to, can I have someone to read out the first couple parts of this problem? Can I have volunteers? Can I have 3 volunteers? Miata is number 1. Chelsea is number 2. All right, Miata, go ahead and read that first bullet.
Unit of a chemical company is studying the reaction of CH4 and H2S, 2 compounds of natural gas.
Okay, and then we have a balanced equation where methane reacts with hydrogen disulfide to generate carbon disulfide and hydrogen gas. Chelsea?
In one experiment, 1 mole of CH4, 1 mole of CS2, and 2 moles of H2S and 2 moles of H2 are mixed in a 250 milliliter vessel at 960 Celsius. At this temperature, K condensation constant is 0.036.
So I want you guys to determine what direction this reaction is going to go. All right, so let's bring it together for a second. Let's talk through this, make sure you guys are on the same track. In order to use, let's go really high level. What are we doing to answer this question specifically? What have we done to answer this question so far? Thomas? We need to find Q. Can we find Q with moles? Can we use that equilibrium expression with moles? No, not at all. Anytime we use Q or K, it has to be concentration, which is moles per liter. So make sure if you've already tried to find Q, but you've done it using moles, you go back and you look at that and use molarity instead of moles. Once you've done that, you can answer this question, and then you can start filling out the table below to figure out what is the exact concentrations that we get at equilibrium. All right, so we're running low on time, so I want to make sure that we talk through this and set you guys up for the next problem. So in order to answer this question, we need to find the concentration of all our reactants and products. Do we divide the number of moles by 250? By what? By liters, so 0.25. Okay? So we go ahead and we find our concentration of all of our reactants and products. So I have 4 molar, 4 molar, 8 molar, and 2 molar. 8 and 8. And then we use that to find QC. Sarah, what did you find for Q? Val, did you? That's what I got as well. So are we at equilibrium? No, we have a much bigger number than K, so that means that we have to generate more reactants or products. It means the reaction is going to go from more products to more of the reactants the way the reaction is written. So Q is bigger than K. It means the reaction goes towards reactants. Questions? Everybody okay with what we've done so far? Then the question is, when we get to equilibrium, what are those values going to be? So, here's a little piece of info that I don't know if I gave you in the problem. I did give this to you. If we know that our reaction is going to end up with 5.56 molar concentration of methane at equilibrium, how do we solve for the concentration of everything else? How do we use our ice tables to solve for all of that? So we're going to be using these rice tables or ice tables, depends on how you want to talk about it. The rice table says we have a balanced equation or reaction at top. What are our initial quantities, or actually concentration is what we're going to use. What's the change in concentration? And then what do we get at equilibrium? So that looks like this. You guys have this table here. So what do we put in here as our initial concentrations? And we're going to do this whole table in concentration. McKenna, where do we find these values for initial concentration?
4, 8, 4, 8.
So those are the numbers we just calculated. How much change is there going to be? And this is the really hard part. Does anyone want to talk through how we find the change? Brian?
Doesn't it have to do with like the coefficients?
Has something to do with coefficients. So did we say it's going to go to the left or the right first?
It's going to go to the product, so it's going to go to the right.
Do we find who's going to go to the products?
Oh wait, no, the reactants.
Q is bigger than K, so that means that we're going to take some from this side, and it's going to move to this side. So in order to do that, is it adding to the left side or subtracting? It's going to add.
Yeah. So that's going to be.
So then for every one of these that goes away, CS2, how many HS2s are we going to make? Don? We use one of these, we get 2 of these, and 1 of these. So this is honestly the hardest part for every student that starts working with ice tables. 1, what is the sign of our changes? That's Q versus K. And then the second part is, well, for every 4 hydrogen that go away, 1 CS2 is going to go away, and we'll generate all based on the stoichiometric coefficients. And since we know that the equilibrium concentration is going to be how much we started with, how much that changed, we should be able to figure out how much bandwidth. So you guys can go ahead and complete this one, and I want you to take a stab at that last problem on the worksheet, which does the same thing, except we're talking about for something you might have to look up an equilibrium constant value for. All right, thanks a lot, guys. Happy late Halloween.